Okay, can you hear me?
Yes.
Thank you very much. Let's go back to the class now. Today we will start going to the several details that we will discuss in the next lectures concerning the procedures of modeling environmental systems. So today we will recall some of the concepts we have introduced in the last lectures, describing or defining some aspects of environmental systems, and we will start into the details of how to model or to build describing the procedure of how to build an environmental model. In order to do so, let's start by introducing some concepts. In particular, we will discuss now the elements of a model, as we have already said. While dealing with environmental system, we shall distinguish between an external environment and an internal environment. So this point we shall precise, we shall be more definite now. We may introduce the effect of the external environment into the environmental system we are going to model. So the first element of a mathematical model is describing external effects. So the first element is called external variables or forcing functions. So external variables are describing the external environment and the effect that this external environment has onto the system we are going to model. In particular, in order to describe the effect of external environment, we shall introduce external variables, and we shall call these external variables forcing functions. So functions that are forcing or somehow modifying the behavior of a model according to changement on external conditions. A clear example or a very important example of these external variables or forcing function is, for example, the temperature. Temperature is typically one of these variables that describe external environment and have a dramatic effect on the behavior of the model describing the system. When we introduce external variables or forcing function, we shall also give a range of variations of these variables. And as we will see soon, especially when we will describe the effect of temperature or the limiting effects of temperature on the growth process, we will see that we shall introduce some intervals of values of external temperature that will change or govern the behavior of the model. The second element of a model, it is that of state variables. State variables are describing the state of a system itself. Of course, state variables may be dependent or independent variables. Typically, an independent variable is the temperature, in the case it is considered a state variable, or maybe an independent variable, maybe the concentration of chlorophyll A. And dependent variables instead are variables that depends on independent variables. Also for these variables, we shall introduce ranges of variations, so that when we will verify the behavior of a model, we shall have some indication of what are the values or reasonable values for these state variables to be assumed. So the idea is that external variables from the external environment control through forcing function the behavior of the system. So I have, as customary, identified a boundary, internal and external. Internal is described by state variables. External system is described by external variables or forcing functions. And the forcing functions somehow represent the linkage between external condition and the state of the system itself, so state variables. How these linkages are described? These linkages are described through equations. Equations are the mathematical description of interactions between the various elements of a model. In particular, equations describe interaction between state variables, but also interactions between external variables and state variables. Into this equation, we will see that there are universal constants. Universal constants, like for example, when I think of the concept of universal constants, I'm thinking about, for example, the speed of light. It is a prototypical example of a universal constant. Universal constants are parameters or constants that link the various variables, external and state variables, allowing to put them into the same equation, as ensuring that the units employed for describing these variables are consistent each other. The fact that we employ universal constants ensures that we are summing apples with apples, or pears with pears, as we would say in a colloquial way, so that we employ universal constants in order to be sure that the elements that appear into mathematical equations, that is the third element of a model describing interactions between variables, are made up of elements that are consistent, at least in terms of units of measurements. Then the fifth element, that is most important for the ecological modeler, is that of parameters. Parameters may be seen as the control knobs that may be acted on in order to change the behavior of the model itself. At different values of a parameter corresponds different behaviors of the model. So, as you may understand now, parameters are the elements of a model on which the model has the opportunity to act in order to change the behavior of the model, and we will soon see what we mean by that. Of course, I anticipate I'm talking about calibration. Okay. During this lecture, we have introduced several different model types. And model types may be classified in terms of, for example, the objective of the model. Research and management models are two different model types. Research models are used for scientific investigation, while, for example, management models are used for building support application or management tools. Another important classification we have seen during this lecture is that between deterministic and stochastic model. Deterministic models are the classical mathematical models we are used to employ when, for example, we deal with physics. And deterministic models have a defined, or we may say exact output, while on the contrary, stochastic models include some kind of randomness or variability, uncontrolled variability into a model. And in this case, the output values of the model are described by probability distribution, or if you want, clouds of possible value. The third important classification we have looked at is that between compartmental and matrix model. Compartmental models are models in which state variables are associated with time-dependent ordinary differential equation. And we will see later what we mean by this when we will start talking about the mathematical implementation of a model. Another type of model is that of matrix model. Is a different way of representing ecological systems. In this case, the relationships between the variables may be described by matrices, and we will see that by employing these linear algebra tools, that is matrices, we may end up with a quite easy and efficient way to describe complex systems. In this case, the relations between the various variables, state variables or external variables, are described by matrices, and we will soon see some example of this. Another important classification of mathematical models that is more related to the epistemological perspective that my model employs is that between reductionistic and holistic models. We have said that reductionistic models are models that in which the model try to include as much as possible details concerning the system, while on the contrary, holistic models are models in which starting from principle of a maximum generality, the modeler tries to introduce descriptions, um, holistic description of complex system. The typical example coming from physics of holistic models is thermodynamics. Thermodynamics is typically an holistic approach in the description of complex systems. I recall you that in thermodynamics, essentially, we use three variables that are temperature, pressures, and volumes for describing systems that may be of a large level of complexity. We will then precise more in detail what we mean by the concept complexity, because we will give soon a way of measuring the complexity of a system as well as the complexity of a model. Another important classification is that between that differentiates between static and dynamic model. Typically, in static model, we shall be able to find at least one state variables that do not depend on time. We refer on static model often with the term stationary models. Stationary models are models for which we may identify a set of state variables, but sometimes also a set of external variables that do not depend on time. So for which we may formally write that the derivation in times of these variables is equal to 0. So these variables are constant in time. On the contrary, a dynamic model is a model for which this assumption does not hold. In this case, state variables depend on time. So state variables are dynamic description of the evolution of the system and are function of time. Again, we will see some example of these descriptions. Finally, another important distinction is that between distributed and aggregated parameters model. This classification has to do with the definition of scales, as we have said a couple of lectures ago, when the modeler starts to build his description of a system, he is faced principally with the definition of spatial, and temporal scales. In this case, if we build a classification of these models, we immediately shall distinguish between models for which the parameters are function of time and position. So these are distributed parameters models. So parameters changing according to the different places and times of the system that we are describing. On the contrary, the opposite condition is that of aggregated parameters models, in which we have constant parameters with a certain spatial temporal limits. So defining certain spatial and temporal limitation, inside these limits, we may consider the parameters constant. You may understand that these are, again, approximation. Of course, aggregated parameters models are easier to treat compared to distributed parameters models. As well, static models or stationary models are easy to be described than dynamic evolutionary models. Again, the reductionistic models for which I may understand the behavior of a complex system by understanding the behavior of the subsystem making up the totality of a system, instead are easier to treat and to describe compared to holistic models, in which we shall find general principle or principles of a maximum generality in order to describe the behavior of a system. I recall you again, when I think at reductionistic and holistic model, it comes immediately in my mind. A reductionistic model is, for example, a model that gives you the coordinates of a particle as a function of time and positions, while in a holistic model, instead, we try to link the behavior of a model to parameters that describe in general terms the system. And this is the case, for example, of thermodynamics, in which we may try to employ temperature or volumes to that are macro holistic descriptors of the system to describe the evolution of a complex system. From a mathematical point of view, we have forward distinction or classification. The most important one is that the distinction between distributed and aggregated parameters model. In the case of distributed parameter models, or models in which the parameters depend on the time and position, we typically employ partially differential equations, as I have to try to synthesize by this writing here, which we have derivatives of the state variables onto the different spatial coordinates, for example, derivatives in x, derivatives in epsilon, derivatives in z, but as well derivatives in the temporal coordinate, derivatives in times. Why, in the case of aggregated parameters, in which we employ a simplified description, we typically employ what are called ordinary differential equations. In this case, you may have, for example, derivatives of first, second, fourth, and nth order of the state variables that are combined in order to build the mathematical description in terms of a system of equations, systems of differential equation. Please remember, in partial differential equation, typically we employ first order derivatives, as is the case, while in ordinary differential equation, we may employ different order derivatives, first, second, third, and so on derivatives. Okay, I hope that you have already seen this kind of formalisms. In reality, I should confess that I'm assuming that you already understand these kinds of writings. You have seen these writings several times during your student career in different contexts, in different classes. I'm trying to summarize this all up in the context of environmental systems modeling. Let's go on with forward classification or differentiation. As we have already said, we may differentiate ecological models or system models in terms of their mathematical basic assumption. For example, a first distinction or classification that may come to our mind is that what distinguishes between linear and nonlinear models. Typically, linear models are described by first order differential equations. So if we go here, we may employ ordinary differential equation of the first order in order to describe linear model, as well as if our mathematical description is made up in terms of distributed parameter or partially differential equation, then in this case as well, you will employ first order differential equation to describe linear system. So typically a linear system is described by first order differential equation. Nonlinear systems, on the contrary, are systems in which one or more of equations are of higher order than the first, higher differential order than the first. So in nonlinear system, we may find also more than the first order derivatives differential equations. From the epistemological point of view, we may also distinguish models that may be defined as causal or black box model. In the causal models, that are the reductionistic type models, Cartesian, if you want, a Cartesian approach models. In this case, we may identify causal relationships between inputs and output state description. So input and output of the systems, input and output states of the systems may be linked by causal relationships. So in this way, we are assuming that we are able to describe in mathematical terms, in explicit terms, the linkages between the state of the systems and the changement of the external conditions that may act on the state of the system. On the contrary, black box models are models in which the uncertainty of inputs is directly reflected on that of the outputs. This means that in black box models, we renounce to describe with an arbitrary detail what is happening inside the box describing the model, and instead we simply employ probability distribution that may link the inputs to the outputs. And these probability distribution are, if you want, a way of formalizing the mathematical uncertainty related to the variables we employ to describe the system. In practice, the most mathematical models you shall employ to describe complex environmental systems are in between these two extremes. So are in between causal and black box models. So we try to be causal when we can be causal, and instead we shall be black box when we do not have enough information on the processes that we are describing. And in this case, we resort in using probability distributions. In practice, the models are in between these two extremes, and we may call these models gray box models. Gray box models are models that are partially causal. So we are causal when we can be causal, and we renounce to be causal, and instead we are black box when we shall employ probability distribution because our knowledge of the system is very limited. Another important mathematical distinction that brings with the classification of different modeling approach is that between autonomous and non-autonomous systems. Typically, in autonomous systems, differential equations do not depend explicitly on time. So we may say that the derivative in time of, for example, the state variable vector is constant and equal to a function of the state variables, but not of time. So time doesn't play a role. We are renouncing to make an explicit time description, time evolution description of the system, while in non-autonomous system, we may find that differential equations depend explicitly on time. So this is formally written by writing that the derivative in time of x, that may be a state vectors, state variable vectors, the derivative in time of x is equal to a function that explicitly depends on time. So this linkage, this means that the linkage between the various elements of a model, state variables or external variables, may change in time, and this changement is described by this function of the state variables and of time. Again, there are distinctions that depends on the objective of the model. In particular, for example, if you are building a demographic model, in this case, we may employ, for example, principles of the maximum generality, that may be that of the conservation of information. And in this case, when I'm thinking of conservation of information, I'm thinking on the genetic code for example, the genetic code that is containing to the genome. In this case, we assume a kind of conservation of information in terms of number of individuals and informational content carried by these individuals, described by the genome you may find in these on the elements of your model. Again, we may find another type of description that is an energetic description. In this case, we may employ the principle of conservation of energy. In this case, the state variable may be energy density, joules per cubic meters, while in the case of demographic models, the state variable may be the number of individual or the informational content of the genome carried by this individual. A third type of model may be that of a chemical model in which we assume as a principle of the maximum generality the conservation of mass. In this case, typically, the state variable is the density of matter, for example, milligrams per liters of something. And this is a very typical model that environmental engineers employ to describe ecological systems, because in this way you have a straightforward indication on how to measure the quantities that you shall employ for describing your system. Typically, density of matters, you may think, for example, on a CSTR model, continuously steered tank reactor, in which typically the state variable is that of a density of matter. Or, for example, you may think if in your reactor, you're describing a process of growth, primary production growth, then one of the state variable, in this case, may be the density of nutrients that may sustain algae growth. Again, this is important to keep in mind that according to the epistemological approach or description we want to include in our system, we shall select the appropriate currencies. In the first case, the currency is the number of individuals. What is flowing between the elements of your model is a number describing the number of individuals or the information content of the individuals. In the second example, the case of energetic modeling based on energy conservation, then what is flowing between the elements of your model is energy. So you shall employ, for example, as a currency for your model, energy density, joule per cubic meter. Finally, in case of a conservation of mass approach, then you shall employ as a currency the density of matter. So what you will look at flowing between the elements of your model is density of matters, milligrams per liters. Let's first of all introduce the more more simple description of a system. For example, let's give a look at linear models. We have said that in the case of linear models, we may employ linear algebra. So we may employ the matrix representation. And I, for example, may decide to schematize my system by introducing 4 elements. These are 4 actors playing into my plot. X1, X2, X3, and X4 are state variables describing the state of a system. And each state variable is linked or is describing one of the actors participating into a plot, and then we shall describe the interactions between these actors in terms of flows or leakages or connections between the state variables. Schematic representation of interaction may be given by these drawings. So we may identify 4 boxes describing 4 elements of my model, and then I decide or I realize that this box may interact each other, and I describe this interaction by drawing arrows connecting these elements. Then it is straightforward to convert this drawing into a matricial representation in which we represent the interaction between the four actors, 1, 2, 3, 4, by including the flows of the currencies between the four actors of a plot. The flows of a currency is described by the numbers appearing in this matrix. For example, if I want to describe interaction between actor 2 and actor 1, then I shall put the number describing the interaction into this box. Please note that these are oriented arrows. This means that if I want to describe the reverse interaction, so the interaction between element 2 and element 1, then I shall describe this reverse interaction by putting number of rows of currencies into this box. This way of representing mathematical models, so in particular linear models, is very powerful from a mathematical point of view because it allows you to describe the evolution of a system, even a complex system, in very efficient mathematical ways. In particular, if I want to describe, if I introduce as a descriptor of the state of a system a vector of 4 state variables, 1, 2, 3, 4, x1, x2, x3, and x4, then through this matricial representation, I'm able to compute the value of the state variables at a time instant that is successive to the initial time instant by simply making a matricial product of a matrix A times the state vector x. Please note that this is a product in the algebra of matrices. This means that it is a product between a matrix and a vector. So this is a column by row product that you may have seen in several conditions several times during your student's career. So this dot, big dot here, represent il prodotto linee per colonna, so the product lines by column, in which you multiply the matrix A times the state vector x at time t, thus obtaining the value of the state vectors of the next time steps. Of course, with a synthetic representation, I'm writing t here and t plus 1 here, meaning t the initial time and t plus 1 the successive time. We may employ various ways of distinguishing this changing. We may, for example, employ indexes or apices or so that, but a powerful point here is that we are describing the evolution of a linear model by employing the product, the scalar, the vectorial product into the algebra of matrices. So we are multiplying vectors toward the matrix representing the interactions between these state variables. I hope this is not particularly new for you because I'm sure you have seen this way of describing evolutive systems in several contexts. And the point is that this description is very powerful in terms, for example, of computational easiness. Employing this type of description allows us to make in a very efficient way calculation on a system that may be very complicated, for example, very complex in terms, for example, of number of state variables. So even if I have, for example, hundreds or thousands of state variables, by employing this mathematical tool provided by linear algebra, I may be able to make studies of evolution of a state of a system. Now, we shall introduce an important topic that will drive us little by little to the conclusion of this lecture. And the topic is that of the problem, the issue is that of selecting the appropriate model. Selecting the appropriate model among all the various, the plethora of various types of mathematical modeling approach that we have been introducing or discussing in this lecture is the task of a modeler, mathematical modeler itself. In particular, in the case of environmental system modeling, it is an environmental engineer typically that starts facing itself with the issue of selecting the appropriate model. The selection of the appropriate model depends, of course, on the problem in analysis. So, which kind of process I'm looking at will give me guidances in order to select the more appropriate model. If, for example, I have very few state variables, I may employ a dynamic complex model. If instead I have a system but for the description of which I need thousands of state variables, I shall try to employ linear approximation, so matrices description. But the selection of the appropriate model, of course, this depends on the targets, so on the systems we want to model itself. So, for example, if I'm modeling a problem or an issue related to eutrophication, then I, in the selection of the appropriate model, I shall consider the fact that I will have to include, for example, nutrient availability, and for example, a description of the quantity of phytoplankton produced into my model. So it will be the target of my description that will help the modeler in selecting the appropriate model. But another concept linked to selection of the appropriate model is that of the model complexity and the system complexity. And as we have said several times, we shall try to find a model that is adequately complex in order to describe the complexity of the system that of a target or of the system that I'm working on. We will see some way of measuring this vague, if you want, term complexity that I've employed several times, and I've tried to describe the most general terms, but also the selection of temporal and spatial scales will be one of the guidelines that will help me in selecting an appropriate model. In particular, will, for example, guide me in deciding if I want to employ a distributed parameter or an aggregated parameter model. So this is the definition of the temporal and spatial scales of my system that will help me in selecting the modeling approach. Another important criteria is that of the availability of data in terms of quantity and quality of data. Just to say that it is useless that I implement a mathematical description of my system with a very detailed description of several processes if I'm not able to gather data on these processes with an adequate quantity of data and adequate quality. Another concept that might guide us in defining or selecting the appropriate model is that of I shall ask myself if I want to include the possibility of structural dynamicity into my model. What is structural dynamicity? Is the possibility of changing the structure of the model itself in time. When I'm thinking of changing the structure and thinking of including a new state variable, so a new actor comes into my plot, or excluding a state variable. So for example, one of the actors of my plot gets extinct or dies or exits from the plot. Or for example, including new relationships between the state variables. So new processes, describe new processes. In this case, I shall employ a new arrow or a new linkage between the state variables, and this brings with itself the changing of the structure of a model. So, for example, if I want to describe the effect of invasive species into an ecosystem, I shall, for example, select a structural dynamics model, so a model that may have the opportunity of changing this wave structure in terms of including or excluding a new actor into the plot, a new subject that may be significant in the description of the system, or the description of my target. Then a final question that the mathematical model may consider is that of employing an object-oriented approach. To object-oriented approach that is typical when you employ individual-based models, in which you are modeling, for example, let's go back and give you the case of demographic model in which you have conservation of information. In this case, each element in the model may be described appropriately by an object-oriented approach. For those of you that are familiar with programming, object-oriented programming are mathematical programs in which you try to describe the state variables as individuals, and the interaction of these state variables among them and among the external conditions are described as methods of interaction, or methods of accessing the values of a state variable. This is the object-oriented paradigm that, especially in IBM individually based model or demographic models, may be the selection of choice. So again, when selecting the appropriate model, the mathematical model may go through a series of questions. May be my model formalized by matrices. This is, of course, the first choice the mathematical model should look at, because this formalization, as I tried to explain you, makes the model very easily treatable in mathematical terms, and makes models of even very complex systems not so cumbersome in terms of computational requirements, or in terms of CPUs, or requirements of computational power. Okay, you can formalize your model by matrices if you're happy with linear relationships. So if you accept that you will describe the relationships between state variables with linear models. Of course, this is often not enough, especially when you're dealing with complex environmental systems. Then the second question that may drive the selection of model is, am I happy to include or to introduce into my model some kind of stationarity, a stationary model? This is typically the case in which you find yourself if there is a limited availability of data. For example, data concerning the target or the system you want to model are costly or difficult to gather. In this case, you should try to be stationary, so to identify some kind of state variables that do not change in times, or some kind of characteristics of a model that do not change in time, so whose derivatives are zeros, or derivatives in times are zeros. Of course, this approach provides only an average response, typically a seasonal model in which you may simply introduce four stanzas into your plot, and these four stanzas maybe are spring, autumn, winter, and summer, the seasons. And this is a choice in particular. It is a need in particular if you are going to model systems that have present large spatial scales, like for example, if you're going to model landscape processes or for example, river watershed processes, that are processes typically of large time and spatial scales. Then you may ask yourself if you may be happy with probabilistic approach, so probabilistic models. In this case, again, if you are in a condition of limited availability of data, this may be a choice. In this case, you will have only clouds of probabilities as output of your model. So you are renouncing, you are giving up to have an arbitrarily detailed answer or output of your model. Instead, you are happy with clouds of probability. Then you may ask yourself if your model is to be formalized by differential equations. And this, we are going to a more deterministic, reductionistic approach of description of the systems. So if I need to include differential equations, so this means that I want to describe spatial and time evolution of the system. In this case, you need large amount of data, typically of good quality, but in this case, you may be able to describe the evolution of your system in time and space. So you are looking for times and space dependent outputs of your description. Then you should ask yourself if you need to include structural dynamicity. Again, you need a large amount of data, typically of good quality, but this is a choice if you want to describe, for example, evolving systems, as I have introduced before. If you want to describe a system in which evolution may allow to come into a play new species, then you are forced to employ a structural dynamic model, so to include a way of changing the structure of your model into a model itself. And then you may ask yourself if you may be happy with an object-oriented approach. In this case, typically, you shall be able to consider the individual as the base unit. As I told you, this is the choice when you are including or you are describing IBM individual-based models, demographic models. So, we conclude the lecture of today, trying to define more precisely what we mean by an appropriate model. When I think to the appropriate model, I think to a model whose complexity is adequate for describing the complexity of the environmental system I'm looking at. The appropriate model is reliable as the least reliable of the inputs. So please take into account the fact that your uncertainty on the inputs of your model will be propagated to the output of the model. So you're looking for a reasonable compromise on the complexity of the different submodels, a reasonable compromise of the complexity of different submodels, but anyhow remaining able to describe the complexity of the whole system. The idea is that of being as simple as possible with the minimum required complexity. So complexity is a way of evaluating the appropriateness of your model, but is also a way of evaluating the computational or logical effort needed by the modeler in order to build up your description. An appropriate model, so appropriately complex model, allows you to obtain a better understanding of the system. It is not necessarily as reliable and quantitative prediction, so we are in a kind of uncertainty principle condition in which we have to give up uh, our pretend. We are not pretending to describe my system, the system, my target system or the target system with an arbitrary complexity or with an arbitrary precision. Instead, we are more searching for a model with the appropriate structure in terms of complexity to describe the complexity of the system or environmental system that is the target of my study. We need a systemic approach. The model is not a reality, of course, but it is just an attempt to represent certain elements that are peculiar to the system. Which are these elements? It will be the modeler that will select these elements according to a target or objective of the model. So, for example, if my model is a nutrification model, we shall include into the model, for example, nutrients and chlorophyll A concentration, but we will neglect several other aspects that may be significant for the description of the processes, but it may complicate or make the description too complex according to the target that I want to describe. I will now conclude my lecture by introducing the procedure that we will describe in detail for building a model. We have identified 8 key steps: problem definition, model conceptualization, mathematical formulation, verification of the model, numerical formulation, sensitivity analysis, calibration, and validation of the model. All these 8 steps will be discussed in details in the following lectures. Problem definition. So we look at the problem we want to describe. For example, as I told you, the example of eutrophication. So we look at the problem and we look at the data available for describing this problem. For example, eutrophication, how much data I have concerning, for example, chlorophyll A concentration. Or, for example, if the problem is building structures for flood control, how much data I have on, for example, precipitation, or how much data I have on land cover, and so on, or how much data I have concerning groundwater. Then you have to choose the limits and spatial and temporal scales. And then you have to identify the subsystems. For example, in the case of eutrophication model, one subsystem will be algal cells. So one of the subsystems may be that of an algae that is growing. So a subsystem may be the description of nutrient assumption and growth process as a consequence of nutrient assumption. Then, when you have defined appropriately your problem, then you switch to the next phase, that is model conceptualization. In this case, you start to put in your hands into the mud, as we say. So you identify the forcing function, you start identifying state variables, you identify functional relationships between these elements, you start to design a conceptual diagram, and this is the moment at which you start measuring and identifying the complexity of the model. So the process of the step of model conceptualization is the step is the point at which you try to translate your problem, you define the problem, you try to translate the problem into a kind of conceptual description. So you identify the subjects, you identify the actors on your plot, and you identify the relationships between those actors. Once you have conceptualized your model, you are ready to switch to mathematical formulation of a model. Then this is the point at which you start writing equations for its relationships, connecting the various actors into the plot. You identify constants and parameters. So this means that you try to be sure that you are making mathematical calculation among elements that may be mathematically compared. So definition of units. Then you identify ranges of variabilities for the parameters. I recall you that the parameters as the fifth element of our models are those elements that you act on, so calibration knobs or knobs that allow you to change the behavior of a model. This is the point when you do a mathematical formulation in which you have to be sure that the parameters may be made vary into well-defined ranges of variabilities. And then this is the point at which you introduce the mathematical formalism, ordinary differential, partially differential, linear, matricial representation, so all the concepts that we have discussed up to now. When once you have formalized mathematically, you are ready to verify the behavior of your model. You start the resolution of differential equations. You analyze the gross behavior of a model. So, for example, you verify that the model is behaving as you are expecting behaves. For example, temperature increases when dissolved oxygen concentration decreases. So, just to give you an example, but you may find an enormous quantity of this kind of examples. So you are verifying that your understanding, your knowledge of the system is correctly implemented into the model. This is why you need verification. Once you have verified your model, you are ready for the numerical formulation. So you now choose the programming language or the software tools. Typically, here the environmental engineers employs MATLAB, that is numerical environment in which it is quite easy or it is comfortably translated the mathematical formulation into a numerical formulation. Then when you have the numerical formulation, your model, your creator, the newborn creator that has been produced by your brain is ready to be studied. So you start the very important task of sensitivity analysis. During sensitivity analysis, you start understanding how your newborn creator, the model describing the environmental system, is behaving. How do you do that? You do that by changing the values of parameter forcing function or other aspects of the model, and you analyze how the model changes its behavior. This phase, it is very important, is a prerequisite phase in order to proceed to the next phase, but is calibration. Calibration, you are resolving the equation of a model, you are comparing the results of your model with experimental data, and you are changing the values of the parameters in order to find optimal values representing the experimental data. This is the step of calibration. Once you have finished with calibration, your newborn creator has gained the status of self-consistent mathematical description of an environmental system. And then you are ready to make the step forward, that is the validation of a model, that is applying the calibrated model onto different systems to verify that the model works, or to ask yourself if you have to vary some parameters in order to make your model more able to describe a larger number of systems. So validation means applying your model to systems different from those that you use in the calibration phase. So you calibrate your model in a particular system, then you validate your model by applying the model onto a similar system, but different but similar, another system, but with some kind of similarities. For example, if your model is a model lake, then you will validate is a lake model based on the phosphorus currency. Then you will try to validate your model by applying it onto a different lake, again with phosphorus currencies. Finally, once you have your newborn creator model, you shall ask yourself a series of questions that are of, if you want, of practical value. It is the model stable, or the model will degenerate its behavior there, or have some kind of deviations that may move the behavior of your model. Please keep in mind that we are describing systems that may change their behavior in time and space. So in this case, you may find yourself with a newborn creator that is behaving in a absolutely non-logic or non-unexpected way. In this case, the model is not stable and may be not so useful for being applied onto real system. The second question that the model typically poses itself is, does the model respond as I expected? Meaning, have I been able to include into my description my understanding, my scientific understanding of a system? If a model behaves in an unexpected way, then you should stop and ask yourself, pose yourself some questions and go back to the formulation, to the conceptualization of a model. And finally, typically you ask yourself, is the mathematical formulation consistent? So I'm summing peers with peers and not peers with apples. So I am comparing or combining things that may be consistently combined in terms, for example, of units. Are the equation formally correct, the differential equation formally correct? These are all practical issues or questions that the mathematical modeler may ask himself in order to verify the functionality of its model. And by today, we stop here. If you have any questions, I'm ready to answer to your questions.